Welcome to MRS Bulletin's Materials News podcast, providing breakthrough news and interviews with researchers on hot topics in materials research. My name is Laura Lay. Polymers are widely used recyclable materials, but there are fundamental unknowns surrounding their properties. New curiosity-driven research from the Georgia Institute of Technology has focused on what happens when yielding occurs under uniaxial tension and has led to a surprising discovery. After the material undergoes necking, its response under certain conditions is independent of strain rate. This behaviour is markedly different from the virgin material, which is known to have a response that depends on strain rate.
We pull the material on uniaxial tension, and then normally when we see that a material yields, this means that basically it kind of fails. But in our case, we focused on this material, the yielded material, and then we characterized this material as a new phase. So it's kind of like a cold drawing process where we applied a force, we yielded the material, we created a new material state out of the same polymer.
That was Assistant Professor Christos Athanasiou. Using polyethylene tetraphthalate in a large load cell, different strain rates were applied. The necked part of the sample was then cut out and retested at different orientations. Retesting with the sample oriented transverse to the original draw direction, the polymer exhibited reduced yield stress and secondary necking. In contrast, material retested along the original draw direction was found to have a yield stress more than double that of the virgin material and an increased elastic modulus. Lead author of the study, postdoctoral researcher Danchi Sun, explains further testing to link this behaviour to changes in the microstructure.
Along the parallel direction or the draw direction, this material is enhanced by more than 2 times. So we are very curious how about the other direction, how we found that, wow, this material is highly anisotropic. We want to see if this highly oriented material state leads to its extraordinary mechanical behavior and the rate independence. So we also did some material characterization like DSC, to see if the crystallization or the highly oriented microstructure leads to this chemical behavior.
The differential scanning calorimetry revealed that although the virgin material exhibited both a cold crystallization peak and a melting peak, the necked PET produced only a melting peak, which indicated that crystallization had occurred as a result of being put under load.
During the stable necking process, the polymer chains in the yield material has aligned along the draw direction, and this leads to the enhanced intermolecular interaction between the polymer chains, and this interaction supplies chain mobility. So its rate dependence and other viscoelastic behavior is suppressed. And also this material state leads to an enhanced chemical behavior along the draw direction.
Putting the material under strain, which causes necking, leads to a new material state which could be used as a new way of manufacturing polymeric materials with highly desirable properties.
The initial PET is rate dependent. How fast you apply the load gives you a different response. But now the new material state is rate independent, which is pretty unique. Also, it's anisotropic, and in one direction it has very high strength. High specific strength. And this strength can be used, for example, you can think of making composites and using this as like a barrier film, or you can think of like composite layouts where you create this new material state and then you lay materials one on top of the other in different orientations, and then you can create a composite with very high strength.
So far, work has focused on conditions below the glass transition temperature, where polymer chains have low mobility, requiring a large load to be applied. Future work can consider the effect of temperature to optimize processing of the polymer. This work was published in a recent issue of the Journal of the Mechanics and Physics of Solids. My name is Laura Lay from the Materials Research Society. For more news, log on to the MRS Bulletin website at mrsbulletin.org. Follow us on Twitter at MRS Bulletin. Don't miss the next episode of MRS Bulletin Materials News. Subscribe now. Thank you for listening.